Hello everyone, my name is Akif Raja Zahirudin. I'm a PhD student doing aerospace engineering here at Penn State. I would like to start off by first thanking the Penn State Center for Acoustics and Vibrations for having me at the CAV workshop this year. I would also like to thank the CAV leadership for this opportunity to share our work. So today I'm going to share with you our experimental work on the characterization of anti-phase asymmetric rotors. So this preliminary experimental characterization at Penn State was part of a collaboration with NASA Ames Research Center. So the team at NASA Ames developed the concept. They then tested multiple concepts designs using CFD and then chose a design to send to us. So then Penn State was tasked to 3D print these concept blades and then test them out. So I'll try my best to describe how and what we did and go through some of our results. I would also like to acknowledge my co-authors for all their efforts and help in this work. Okay, so I will share with you some of the background and the objective for our experimental work, the experimental setup we have developed to test out this concept at Penn State, some uncertainties that we've determined from our work, uh, and then the experimental data. Okay, so UAVs are rapidly being adapted and used in today's world. And the FAA is also predicting an increasing commercial UAV market. These UAVs will then start to land in urban and suburban areas. And once you have that, you have 50 of them flying on top of your house, you would want them to be somewhat quieter, right? So there is an increase of interest in reducing the noise from all these UAVs. So carrying over that drive to reduce the noise, the team at NASA Ames developed multiple rotor concepts that reduces the noise. So they took inspiration from the turbomachinery industry. One of them is the circumferentially varying status tagger angles that alters the blade forcing function and then allows for attenuation of resonant vibration. So they hypothesized that if the harmonic reinforcement of the rotor blades were disrupted, there is potential acoustic attenuation benefits. So multiple concept designs were created and then tested with CFD simulations. So the most promising design was then passed on to us to be tested at Penn State. So our objective with this work was to experimentally explore the possible acoustic and aerodynamic performance benefits of these trailing edge modified blades which they had developed. We wanted to determine the acoustic behavior in hovering, in static air, and also in edgewise flight. So we want to also get the thrust, the torque, and the combination of the two in another metric that we call inverse of power loading. So in order to do so, we've developed our own test setup. You can see a picture of the asymmetric rotor. It's 18 inches in diameter right there. Our whole test setup, we tested it in our open jet anechoic chamber at Penn State. We also constructed a 1 meter radius microphone array. So this microphone arc was able to rotate on its post to allow the capturing of a 360-degree experimental acoustic sphere. The microphone array is placed at 90 degrees azimuthal location as defined in the picture on the right. And because of pre-existing equipment in the chamber, we are only able to test angles from 0 to 180 degrees. We then populate our microphone array with half-inch microphones and windscreens at those zenith angles you can see. There were 15 microphones in total spanning all throughout the arc. Here are some of the pictures of the microphone array being set up in the chamber. As you can see, it's quite big. And these are our sensors. So we used thrust and torque sensors and then also a optical RPM sensor to capture the RPM of the motor. Next are our blade types. So we tested 3 different blade types or 3 different trailing edges. The baseline is one, and then 2 modified trailing edges, one called symmetric and the other one is asymmetric. So for the symmetric design, the 2 blades, the 2 trailing edges have the same shape, while for the asymmetric, one end has a base trailing edge and the other blade has a out of phase trailing edge. So we have 2 directions, clockwise and counterclockwise, and the counterclockwise is exactly the mirror of the clockwise blade. So a total of 6 blades for this study. All the blades are 3D printed using ABS material, and then the blades are also fixed pitch. So we can only change the thrust values if we change the RPM. We tested two run conditions, hovering and also edgewise at 9.8 meters per second. Sorry for the typo. So the array is always placed at 90 degrees for this test. The clockwise blade, we call it the advancing side because the wind, when it turns clockwise, the wind hits the leading edge first when it spins. And the counterclockwise blade is called the retreating side because the wind hits the trailing edge first when it spins. So you can imagine if we superimpose both of them on one plane, this retreating side is actually as if you have another microphone array at the 270-degree location. We did this because we had a limitation on the angles that we are able to test in the chamber. So these two blades will allow us to capture the acoustic behavior at 90 degrees and 270 degrees azimuthal angles. So it is noted in our test there are possible and multiple sources of uncertainties. Because we tested two sets of the same trailing edge designs, so one clockwise and the other one counterclockwise, it is important to check that these two blades are the same, acoustics and performance-wise. So like I explained earlier, imagine if we put the real and the imaginary microphone arc locations together in a plane of in a side view, the real being the 90 degrees and the other one at 270 degrees. Now we have the picture on the right. So we would have 2 points of comparisons for the acoustics. It is at the axis of rotation. So ideally, microphone 1 and microphone 15 on both arcs should give you the same value. We attempted to compare the OSPL values at these microphone locations. For hovering, microphone 15, which is at the bottom of the arc, it was always saturated, so we didn't compare that. So the highest discrepancy that we saw was up to 0.3 dB in matching RPM case and 2 dB in the matching thrust case. I would direct you to the paper for more details, but just remember these uncertainty values for these cases. We also compared the edgewise flight cases. For here, the uncertainty was slightly higher, 1.8 dB and 2.3 dB. So it is identified there are manufacturing uncertainties from the 3D printing that will affect our results later. So as we were testing indoors, an important aspect to pay attention to is also recirculation. We're not the first ones to test indoors. NASA Langley, for example, has studied this issue in their facility. So at Penn State, a single rotor hover study was carried out to compare SPL values indoors versus outdoors. From our study, this study determined that the SPL peaks within 2000 to 4000 hertz had a region of similar values indoors versus outdoors. So that's why we then selected this region for our preliminary experimental characterization. Although this recirculation issue is still important, but this study focuses on the deltas comparing to the baseline blade. We also allowed for 5 minutes between each test to let the facility reset. So having all of those in mind, let's talk about the preliminary experimental results we've determined from our new test capability at Penn State. There's a lot of things, but I will attempt my best to describe the performance, OASPL directivity, and the SPL results. So we did two series of cases, matching RPM and matching thrust. Matching RPM is mainly to determine the performance benefits compared to the baseline design, and matching thrust cases are mainly done to determine the possible acoustic benefits. So first and foremost, let's look at the hover cases. We want to look at the thrust, the torque, and focus then on the metric combining the two, which is 1/PL. 1/PL is 1 over power loading. So it's also thrust over power. So introducing this modified trailing edges, the symmetric and asymmetric design, we saw a thrust gain of about 10%, but also at the same time, also an increase in torque. Here we get a negative 1/PL value. The matching thrust cases also had a negative 1/PL values. So there are not many benefits in performance when we introduce these trailing edge modifications. Moving on to the directivity plots, the microphones near the bottom of the array are saturated because of the downwash blowing down. So hence the picture is as seen. So modified trailing edges in both matching RPM and matching thrust are actually louder in OASPL than the baseline blades. For hovering, the experiment doesn't show much benefits in acoustics or in performance. So let's move on to the performance of the advancing side blades. So the advancing side blades are the clockwise blades. Here we start to see some improvements comparing to the hovering case just now. The 1 over PL value are now improving. So it becomes smaller compared to hover in both matching RPM and matching thrust. The directivity plots appear to be as shown, and the bottom right is the comparison of the matching thrust case to the hovering case. So we don't have the saturated microphones now because we have wind now blowing, right? So comparing to the baseline blades, most microphones in the matching RPM cases show no acoustic benefit, right? And in the matching thrust cases, they show a slight benefit, but all of these are still within the uncertainty value. Remember, 2.3 dB from earlier. So it is hard for us. We can't make a conclusion because of that high uncertainty value because of 3D print. Now let's take a look at the SPL comparison. So this SPL comparison is done at the 30th harmonic of the BPF. So we selected this harmonic as it is within the region of the similarity in our study. So at the same RPM, the modified blades were louder than the baseline blades of up to like 2 dB. And for matching thrust cases, the benefits here appear to be small, only minus 0.5 dB. Lastly is the retreating side or the counterclockwise blade. So for this retreating side, this is where we saw the most benefit in our preliminary test. The percent difference in 1 over PL is more significant compared to the advancing side. As you can see, the numbers now become 20 something versus minus 2.3 for the matching RPM case. And then for the matching thrust case, it's also 20 something versus 4 and 14 versus 8. This is the most significant thing that we saw from performance side. The directivity plots then look different from the advancing side. Here we can see some microphone locations have acoustic benefits in the matching RPM cases. But again, they are still within the 2 dB OASPL uncertainty because of the 3D printing. So that 3D printing is definitely an issue in our case. In the matching thrust cases, most modified blades show that they are louder than the baseline blades. So moving on to the SPL comparison, this is where we saw the most potential benefits. So the modified asymmetric and symmetric rotors were up to 4 and 5 dB quieter than the baseline rotor. So comparing this to the advancing side, this is very, very interesting. So this gives us a reason to further look into this design in more detail in the future. So as a summary, we've developed our own acoustic test system that is able to test new and novel rotor designs. From those, we are able to look at performance as well as the acoustic data. So from our initial test, we saw that the performance and the acoustic benefits of this asymmetric and symmetric modified trailing edge in hover are quite small. So we started to see more and more acoustic and performance benefits as we move on to the edgewise flight cases compared to hover. The retreating side edgewise flight cases show more possible benefits compared to the advancing side cases. Here we saw benefits in SPL comparison at the 30th harmonic of the BPF of up to 4 and 5 dB. Even so, those gains are related and are affected by the uncertainty, especially from the 3D printing of the blades. So although based on CFD, this concept of anti-phase asymmetric trailing edge modification and symmetric trailing edge modification continuously to be promising, we can't make a conclusion yet from the experimental results. Further tests are planned to look into it more. So we now have developed the tools to further test this blade concept, and the only thing to do is to repeat the test with tighter printing tolerances. So building upon this summary, there are some things that we plan and are working on. Definitely number one is to improve the 3D printing of the blades. Number two is introducing some more averaging and A-weighting in post-processing. Also improvements in the test setup and understanding the facility better, such as the recirculation and the expanding of the flight conditions tested. So we are also looking into transient cases that is of interest down the road. Here is an acoustic test setup that I'm very excited to share that we're currently developing with NASA Langley. We will have the capability to control rotor separation and rotor tilt of future coaxial rotors tests. So some special acknowledgements. We would like to thank Dr. Dennis McLaughlin and Dr. Scott Romson for access and help at the Penn State facility, Dr. Thomas Gabrielson for help with mics, Dr. Kenneth Brentner for guidance and assistance in the design of our microphone array, Dr. Eric Greenwood for guidance in the experimental design and post-processing, and also Dr. Nan Nguyen and Dr. Juntao Xiong from NASA Ames for the collaboration on this study. That's all I have. Thanks.